You ready to film another exciting episode of Real Good at Doing Stuff?
I can't wait.
Gotta be more exciting for Tuesday.
I can't wait.
Okay, good. There we go.
And that, Greg, was the first time I strangled a hyena with my bare hands.
He deserved it.
He did.
I hate him.
Anyhow, you guys, we're here for a new episode of Real Good at Doing Stuff. This is going to be yet another series that I'm starting. If you have too many, what do you do? Start another one. Right?
Exactly.
So this is going to be the first of my interview series, extreme tactical interviews that I've been talking about for a while and haven't got around to. Today, we're finally doing it. So people are going to be super lucky today because it's like a twofer. Today we're going to have two people that are real good at doing stuff. Me being one, and this is, who are you?
I'm a nobody. Oh, I'm Greg Slack.
Right. This is Greg Slack. And for people that don't know, Greg is, in my opinion, one of the world's preeminent racing torque converter people. And Greg builds some of the finest torque converters for racing that there are. If you don't know who Greg is, he's kind of a low profile guy. He doesn't have a big, huge, flashy website and a bunch of people answering the phone. But his work is very well known. It's in some of the fastest stuff that you know about, even though you may not know the converters in there. And sometimes people don't admit the converters in there very frequently.
Among multiple countries as well.
Right, all around the world. It's top-notch stuff. Anybody who's a big-time torque converter guy knows who Greg Slack is. And we've been friends for a long time. How long have we been friends, Greg?
Well, before I got sick with cancer quite a while, so I'd say at least 20 plus years.
Right. Probably since, at 2000 at latest, I would say. Mm-hmm. So a long time that we've known each other. And you'd been building torque converters for quite a while, probably then. You know?
Well, I broke the ice in 1989.
Yeah. Well, how did you get into building torque converters? That's a weird profession for somebody to get into.
Well, I had built practically everything else on my car, and as like most of us, were pretty much, handicapped to have to buy a lot of stuff. I was dealing with a particular company out of another state that had a fairly good sized name, lots of decals and advertisements, and could never seem to get the converter right. And the only one that worked right was filling up my transmission full of metal. And it was a C6. It's one that I had cut for low drag bearings, had lightened it up, and it was very critiqued. It was a fast C6, but I couldn't keep the regulator valve getting clogged up with lots of metal. After the fourth time sending the converter back to get it checked out, I was informed there was nothing wrong with this torque converter. Knowing better, I made a homemade fixture on an old lathe that would hold it perfectly. I would go into that, but I won't. But anyway, I can promise you it held it perfectly. It was so out of realm, 40 thou on the hub, 60 on the core. And when I cut it apart, the turbine, which is this part right here, that rides inside of a front cover, right here on a bearing, was dragging this surface here and the outside because it was so out of round and so wobbly that it should have been a lockup converter because of the amount of contact inside of it.
Right.
And upon calling the guy and explaining to him what I had found, he got really defensive, and one thing led to another. And then I said, if so-and-so, if I couldn't do any better than that, I wouldn't be building torque converters. And that's my suggestion for him. And he said, Greg, that's why you don't build torque converters. Challenge accepted.
Right. So basically, what you're telling me is you build torque converters for the same reason I build engines.
Probably.
You know, if you're going to do it right, you got to do it yourself.
Right.
So you basically you crack the egg here and you open up the first one, and that got the ball rolling.
And I tell people a lot of times that you haven't got to step in the same hole that the man in front of you has stepped in and break your leg to learn anything.
Right.
And not everything is always a forward progress.
Right.
I designed a Stator, or done a funny cut on a Stator one time, felt sure that was going to be it was an OEM style Stator, and I thought this was going to be the great thing. Until we had to nickname it Foobar.
Right.
Because what it done to the rest of the converter was unbelievable. It just did not work. So not every step is always forward, and you can learn a lot more from what you did wrong sometimes than you can do right.
Right. That's a lot of trial and error.
Yes.
I'm sure in this, because, well, let's tell you what. Let's answer a few questions here. First of all, what is a torque converter?
A torque converter is the device that fits between the motor and transmission, and it allows the engine to gain RPM without the car moving. And the job of the torque converter is to multiply your torque. Hence, at a higher RPM, your motor has more power than it has at lower RPM. And the job of that converter to multiply that torque is designed on so many aspects. But the thing that people misunderstand, and what will make stall in a torque converter doesn't exactly equate to more torque. It might make more stall, but it will destroy the efficiency.
Right. Okay. So that brings us to my third question here. Does a torque converter multiply torque?
No. A converter is not going to get any more power out of an engine than you already developed.
Okay.
It's an impossibility for it to make any more power than it already made. But you try to minimize the loss of that power anytime you go through another set of gears. Whatever it be, there's a loss of power. That's why 1-to-1 is generally a more power transferring gear ratio than anytime you roll through a set of gears.
Okay. All right. And you would say that the more efficient the torque converter is, the more we're going to simulate multiplying torque. And we're going to, instead of converting it into heat, we're going to transfer power to the rear tires.
Exactly.
Okay. All right. What information do you need from a customer to build a torque converter for them?
First thing I need is an engine size. I need to know what kind of RPM they're going to operate that engine at, and at what power level it develops. Where it develops that power, at what's the torque and what's the RPM. And then the weight resistance. Weight resistance, gear ratio, tire size all tend to affect how a torque converters work. I get the question all the time, well, what's the stall in this torque converter? That's like asking how much will a rubber band stretch?
Right. Yeah. And so that's something I kind of wanted to talk about. Racers, or you top level racers and real converter guys, don't talk about, don't use the terminology that's in the Summit magazine. That is, this is a 3500 stall, whatever. That's not a word that you ever say.
Nope.
Because it doesn't. The reason that is, correct me if I'm wrong, is because 3500 stall behind what? Behind a 100 horsepower Mitsubishi or a 3000 horsepower big block Chevrolet. They're going to do completely different things, so it's ridiculous to put a. The reason they do that is to sell budget converters to your street crowd, you know. But it's not terminology that racers really use. You say that's correct?
That's correct.
Yeah. Okay. When you build a torque converter, do you give it 100% effort, or do you hold back 10% for the big guy?
No.
Okay.
Everything is 100%.
Around here, it's all 100%.
It's got to be.
Max effort torque converters.
It's got to be.
That's right. Okay. Number 6. This is a controversial, well, to me it's not controversial. Does converter pressure matter?
Absolutely.
Okay. And why is that?
All right, not enough pressure in a torque converter as far as being fed from your system will allow the converter to push more fluid out than it can get in, and that's okay to a certain extent. If that happens for too long and it happens at the wrong rate, then you will develop cavitation, and cavitation is when you have air mixed in your fluid to a point that you're compressing air inside the converter instead of pressing fluid. I just ask people plainly, says, how well does your brakes work when you get air in them? Not too good. Well, a converter, to a certain extent, can literally destroy so much power because there's not enough fluid in it.
Right. Yeah.
I use the illustration, pull a boat halfway up out of the water, boat prop out of the water, and how well does it push?
Right. Yeah. So I kind of compare some of the parts in a converter to a prop, right? And I do a lot of converter pressure manipulation on purpose, right? And what we're doing is planned cavitation, right? We're slipping our prop to achieve a certain goal, right? So when people say that converter pressure doesn't matter, I kind of chuckle.
Yeah, it does matter, and I have a lot of people that'll ask me when they call up about what pressure should they do here and there. I don't keep up. I don't ask Pete what his converter pressure is on his applications, nor some of the Pro Mod Racer, because I feel like that is his
Right.
information to use. I can build the converter, and the fine tuning, that's just like how much nitrous, how much timing. Nope, not
Right.
me.
Yeah, right. Well, it is something that we will talk about sometimes because I like trying to understand the relationship between pressure and stator design or whatever. So it's something that I'm interested in, but it's not something I just want to talk about to anybody about, you know. Speaking of which, why don't we talk about some of these parts? This is a completed converter of Greg's. This is for an all motor. Actually, this is for the Wuhan Super Spreader. It is. So this is the one that's going behind that in very short order. So we'll see this thing in action pretty quick, hopefully. But this is a, what is this?
That is a 7.7, as what I call the size of it. It's a Nissan converter. It's an older model, non-lockup design. It was a front-wheel drive converter, and it's about an eighth of an inch smaller at the turbine diameter than your Opel. And it's a little easier to achieve the stall speed that you want out of a lower horsepower motor than a larger converter.
Right. So this is an all-motor application. If you had 3,000 horsepower, this is probably not going to work too well, basically what you're telling me.
You don't think you're on ice.
Right. Now, would you also say that over the years, as converter technology has changed, converters have gotten smaller for the same power level?
Nope.
No?
Maybe for everybody else but me, I started making them bigger.
Okay. You're going big again.
There's a reason for that.
Mm-hmm. Right. Because I remember when I started many years ago, they were big, you know, for, let's say, a 1,200 horsepower deal, you know. Okay, fair enough. All right, let's look at these parts. What do we got here? What is that?
This is the front cover. This is an OEM front cover out of one 10-inch design core, and we use it because of several things. It was a lockup design converter, and there was a recess in this converter on the inside right here that pushed out forward where the lockup spring mechanism went. It allows us to put a small, thin 3/16 plate in here and take it in place. On the outside of the core, we've got a piece of tubing that's right at 10 inches diameter. We machine down, and we weld all the way around the outside of it here and thin it down. And we set a 3/8 inch thick 360-degree ring on top of that ring, TIG it in, and TIG it to the front where it meets the front of the core here. So basically you have two separate truss areas in there. Those truss areas don't carry weight, and they actually create lots of strength. It's almost impossible to balloon this front cover here.
Right.
Absolutely impossible.
Yeah.
And you can see the machine work in here is It's going to be pristine. It's going to be pristine. And this is machined on a centerless bushing on this plate behind me here. It's a big turn 5 lathe that I have modified everything on it. And this surface, this machine right here, will come into play later in conversation.
Right, okay. And it's important to note, this part here bolts to your flex plate. It always travels at engine speed.
Yeah. A lot of people question why, and actually I had one of the major flex plate companies to call me up and say, why was he getting so many questions and recalls about a 6-pad converter all on 11.5 bolt circle? And I explained to him, he said, you're frankly the reason. I explained to him that if I put this other hole, every other hole in closer, there would not be enough room to put a nut, washer, and everything, and what you need behind it, and hence you'd have a threaded hole, which is going to fail sooner or later. And it's going to be a headache to fix. And this particular company was more than elated to accommodate flex plates made that way for me.
Right. Okay. Moving on. What's the next piece we need to look at here?
Well, the turbine rides in the front cover. This is being driven by the engine. This is being driven by the pump we'll get into later. We've cut the center out of this piece, and we use various precise setups in order to get this new turbine hub spline here centered in it properly, TIG welded in place, and then I come back and all these welds you see is still my job here, is silicon bronze with a TIG, and I anchor all these exits and inlets to keep that fin from working and trying to break loose. I seal up all the holes here so I don't have leakage, and then come around the outside here and weld inside this edge of fin. And what's critical here is I try to make these welds where they're smooth. I don't want a ball of weld just sticking up there because, again, it causes turbulence. This is a smooth transition, and I probably fell well enough to the camera you can see it. It's a smooth transition for the fluid going in here, all these places. Even when they come out in the bottom here, the best I can do to blend it in to make that fluid travel without as little resistance as possible.
Right. Okay.
But this piece has to be straight. If it's not straight, I can't set the clearances on this running to that piece.
Right.
And have what I call grade efficiency.
Right.
So it's very, very straight.
Now you'll notice this part is splined.
Yes.
Because this is what's turning the input shaft
So to your input shaft.
in the transmission.
If this moves and you're in a gear, the car's going to move.
Right. This is what's kind of ending up doing the work.
This is the clutch disc for a hydraulic transmission.
Right. Yeah. Okay. All right. Next. See, I always called this the colander.
All right. Here's the pump. And this controls a lot of the stall speed because, well, first off is diameter. Diameter is the main thing that controls stall speed. The second is the way these vanes are laid in this core. This particular core is considered a positive core because the fins come from the center, and you notice they pitch in this direction. This converter is turning by the engine this way, so it tends to push the fluid in the same direction that your engine is going, which makes a positive converter, which hence is going to be tighter. Again, I weld it down in the base of each one of these vanes here, and I try to smooth it in as much as possible so that the fluid travel is slick. Now, on a lot of cores, I weld to the very top of these fins here so they'll never move again. But if I weld to the top of this vane here, I'm not able to adjust this later for a little bit of stall change. There's some of these pumps that we use that are positive max. You're not going to change them anyway, so we do TIG weld all the way to the top here to stop that from being an issue. This is the vortex ring here that the stator runs in, and this is always sized within 50 to 60 thousandths of the diameter of the stator. The lower vanes on this converter did not necessarily need what we do to a lot of converters have actually a thick. All right, we're going to discuss stators. Stators are the object in a converter that helps redirect the fluid. The fluid comes off this turbine, especially sitting still on the start line. It goes in this direction, makes a turn in these vanes, comes out going the wrong direction. I left that out last time. With it going the wrong direction into this pump here, that's when you have a broken sprag. You don't redirect the fluid and the motor just bogs. You have no power, no torque multiplication at all. In these stators, you will see I've got a 19 window stator here. Here's a 16 window stator, and they're different angles, of course. One of these shows 35 degrees, and one of them shows 29 degrees. Depending on the number of windows and the angle, I come up with various cross sections through here. The cross sections is the amount of area that allows the fluid to get through the stator. My stators are much different in the way I designed them. As far as I know, I'm the only one that uses a deep groove laminar profile on the fins to make happen what I'm looking for. But the more cross section, the sooner this converter is going to try to pull your engine down. Like a fuel car with too much clutch. Oh, it can go fast if you can keep the tires hooked and it's making enough power, but it's too much clutch and you'll either blow the tires out from under it or bog the engine. Not enough clutch and you'll slip all the way down and not transfer the power. But on the torque converters, I have a closely guarded secret of what I'm doing here in order to create the effect that I'm looking for. There's a vast difference between a Procharger, a blower, and a turbo and a nitrous car, and what they require and what they like. Some of the critiques that I do here, if you'll notice that the taper at the end of these stators, I'm always looking for something to reduce the fluid shear, which is it's going to try to make the converter tighter, but it's more important to keep that energy going. Same way with the edge of the fluid coming in this stator. There's nothing to abruptly get in the way. As if you want to look at this stator here, it's one of the OEM stators that's been machined flat on the tops here. Not a good idea. It's going to slow your fluid down. And here's a stator that has straight windows. I call them ceiling fan stators, and they work good. But being the fluids go in at a certain angle and they come out at that same angle, nothing has changed. There's something left on the table there.
Right. I would say that one of the biggest things I've always noticed about your converters is the craftsmanship involved in the stator manufacturing process.
Right.
There are no burrs. Every single thing is well, you can see it's
and there's something that's kind of hard to see is the bottom of this stator here is flared out. This is a 4 inch .250 diameter slug, just like this right here. We get done with it, we turn the body down and to a smaller diameter where it matches up the front of this turbine, so the fluid comes off the center of the turbine and flows right into the stator, and we help turn this fluid slightly into the veins of that pump as it comes out. We want everything a smooth transition. We want that fluid to build as much speed as possible. Give you an idea, I already showed you one piece. This stator here started from this slug just like this. This is a 3-inch ID, 4 1/4 OD, seamless piece of tubing. Whether we're going to do 16 windows or 20 windows, here's the piece that we manipulate. This piece, comes from the laser factory, just cut out, just like this right here. And then we got 7 to 8 different processes to each one of these before they're ready to be tigged into here. Once they're tigged in and I machine it and get the square inches that I want, then we take just a piece of flat blade here that I got a roller over there. I roll it until I get it round, wrap it around these stators, clamp it, and TIG weld everything to place, then machine the bore for the clutch eliminator to go in, and the registers where the bearing's set. And some of these I weld, some of them I don't, but generally it's going to take 15 to 20 tons of pressure to push this clutch eliminator back out of this register here. And I've got a special tool I can set it on, and I got a 60-ton hydraulic press. It won't slip.